So the class tomorrow will be face to face. Okay. Right. Okay. What's my notes? Okay. So for today's class, no more slides. Okay. So today's class, no more slides. So if you don't attend, basically you're not gonna get anything. Okay. So those who are thinking they can study later, get my slides and study later, they are wrong. Okay. Because from now on, no more slides. I'm going to go through. I'm going to go through the class using this Blackboard. So there's nothing I can share with you. Okay, it's only for the first two classes where I've got slides. All right. Okay, so let's start today's class. All right. So now we are slowly. Can you see my screen?
Yes.
Okay, good. Thank you. All right. So from now on, we are going to slowly go into design. Okay, slowly move into design. Now, before I go into design, I just want to remind you certain things that I taught you last week, because it's going to be used today in the class, in today's in today and tomorrow's class. Okay. So first things first. Okay. Concrete, specifically concrete strength. Okay. Oops. So specifically, I'm going to very briefly talk about concrete strength and reinforcement as well. Okay, so from last week, I went through this with you. Okay, FCD. Don't know whether you can still remember or not. FCD is the design concrete strength. Okay, and the formula is alpha CC FCK over sigma C. Okay, alpha CC is to basically convert your cylinder strength, because normally when you get the concrete grade, you do cylinder test. Yeah, you do your cylinder test, you get the concrete strength. Okay, so this alpha CC is to convert this cylinder strength to flexure. Okay, FCK is your characteristic concrete strength from your cylinder test. This is partial. The gamma C is partial safety factor. Okay. Now, alpha CC, to convert to flexure, we use 0.85. The partial safety factor, 1.5. I've gone through this last week with you already. Okay. Now, so basically what you get is 0.85 FCK over 1.5, basically. Okay. Simplified, you divide the 0.85 by 1.5, you get 0.567 FCK. Remember this. Okay. Keep this in mind. Keep this formula in mind. Okay. FCD equals to 0.567 FCK. This is basically the relationship between the two. Okay. Between FCD and FCK. Okay. Now, next. Next, I need to quickly talk about stress strain diagram. Yeah. Yeah. Stress, strain. Okay. Now, the way your concrete behaves is like this. When you load up the concrete, it starts going in. It starts undergoing strain. Okay, the deformation. So as you load it up, it starts undergoing deformation, and then the curve. This curve is parabolic. Yeah. And at some point, it's going to hit its maximum strength, and then it's going to level up. Okay. This point is epsilon C2. And for Eurocode, we keep that at 0.002 strain, okay? So this point, this entire point, the flat part of the graph is basically your FCD. This is your FCD, your design strength, okay? So once it hits the design strength, it also hits, yeah, so once it hits the design stress, sorry, oops. Once it hits the design stress, FCD, it also hits a strain of 0.002, okay? Now, you can keep loading it up, but it will not take any more stress, okay? The stress will stay at FCD, but the strain will keep increasing as you continue loading it up until a point of maximum strain, epsilon Cu2, which is 0.0035. This is when it collapses. Okay. Now, this only applies to concrete in compression. And for concrete grade, less than or equal to C5060. Okay. It's only applicable up to this concrete grade. Okay. Okay. So this is for design. This is basically the parameters that we are going to be working with. Okay. Next. So as I told you last week, okay, reinforced concrete is made out of concrete and reinforcement. Okay, so you also have your reinforcement. So your reinforcement is steel, obviously. Okay, your reinforcement is steel. Okay. For reinforcement, the design steel, the design strength for now we are talking steel, okay. The formula is the design strength for steel make sure you copy this down. If I'm going too fast, let me know. I will slow down. Okay, make sure you copy this down because it's not in any slides that I'm going to provide you. Okay, so reinforcement steel, the design strength FYD is divided by gamma S. I talked about this last week as well. Okay, gamma S, you still remember? This is partial safety factor for steel, which is how much? You remember? It's not 1.5. 1.5 is concrete. For steel, how much? You still remember? Last week from my slides. How much? Anyone? I show it in my slide. There's like a little table on my slide. Anyone?
1.15.
Yeah, good. Correct. What's your name?
Safa.
Safa. Safawati
Yes.
ka?
Yeah.
Okay, all right, okay. Thank you. All right. Okay, yeah, good memory. Wow, 1.15. Okay. Is characteristic steel strength. Okay. So that's the relationship between your characteristic steel strength and your design strength. So basically, what it means is whatever characteristic steel strength you have, let's say normally we use 500. Okay. But to get it design strength, you have to divide it by 5 design strength. Okay. So you reduce the characteristic strength to get the design strength. Okay. By 15%. Okay. So in terms of stress strain diagram, it's a little bit different. Okay. It's a little bit different compared to concrete. Okay. Rather than parabolic, it's a straight line. Steel is a straight line. Okay. And then it hits the U point. Okay. So this design strength is FYD, your design strength for the steel lah. Okay, formula given to you earlier. Okay, and this applies to both tension, steel in tension, and compression. Okay. The modulus of the steel, which is signified by that angle there, is 200 Newton per mm squared. This is the elastic modulus. Yeah, there. It's in the elastic zone. That's why it's called the elastic modulus. Yeah, it's in the elastic zone. Hence, we call it the elastic. Yeah, modulus. Okay. Now, what I'm doing here right now is I'm deriving all the formulas that you will be using later. You need to know where. Okay. Sometimes you may need to modify it a little. Okay. So now we know stress. The formula for stress is this one. I think you learned during applied mechanics or something. Yeah. The formula for stress is elastic modulus times strain. This is formula for stress. Okay. Now we know our stress is FYD, or in other words, it's Fk over gamma S. Modular is the slope is capital E and subscript S. Strain is epsilon S. Okay. Now I can rearrange this thing to get what? What do I want to get? Okay. Epsilon S. Okay. I can rearrange everything to get epsilon S. So basically, I'm going to get Fyk over gamma S over Es. Okay. Now, this is the strain in steel. Generally lah. Okay. Now, when the steel is yielding, at yield, okay, that means gamma S becomes gamma. Gamma, yeah. Sorry, not gamma. Epsilon. Epsilon S becomes epsilon Y to signify that it has yielded lah. Y for yield. Okay. We basically just change the subscript of epsilon to Y. Okay. Therefore, if we use reinforcement, now reinforcement, sometimes I use short form I basically just use a short form to signify steel reinforcement. Rebar. Rebar basically means reinforcement lah. Okay. Reinforcement, steel reinforcement. Okay. Rebar basically means steel reinforcement. The strength of steel reinforcement normally the normal one that we use in design is FYK 500 MPa. MPa is the same as Newton per mm squared. Same thing. Okay. 500 MPa means 500 Newton per millimeter square. Okay. Now this is a characteristic one. Characteristic now. Okay, so to get the FYD, you have to divide by 1.15 lah. Okay. But that's not what we're interested in right now. We are interested in the yield strain. So yield strain is basically FYD divided by the section modulus, which is this from there, section, the elastic modulus, the 200 kilonewton per mm square. Okay. So you get the yield strain is 0.00217. When this is strain, when steel has yielded. Okay. So we have both. We have the strain when steel has yielded. We also have strain when concrete has yielded earlier. Tadi, and the one that I've done earlier. Okay. Now we are going to slowly use all these terms to come up with formula to do our concrete design. Okay. Now next is distribution of stress and strengths across a section in bending or in fracture. Okay. So when we design a concrete section in fracture, okay, we follow a couple of theory. Okay. So the theory is that when we design any RC member, reinforced concrete member, we assume that the concrete will crack. In regions of tensile strengths. And after cracking, all tension will be carried by the rebar or reinforcement. Okay. So in other words, okay, don't worry too much about the wording if you don't understand. Basically, what it means is, okay, I have a beam. I have a concrete beam. Okay. Now, as I told you before, concrete beam, if I don't put any reinforcement, once I apply some loading, it's gonna crack. It's gonna crack here. Okay, it's gonna crack there, where there is tension. Yeah, the bottom part is tension. It's gonna crack at the bottom. Okay. So basically, the approach to reinforced concrete design is we put reinforcement. We put reinforcement there at the bottom. Okay, we put reinforcement there at the bottom, so that when the beam cracks, so we allow cracking. We allow cracking. We let it crack. When the beam cracks, when the concrete cracks at the bottom, the rebar will start to work. Okay, the tension will get carried by the rebar. Okay, so in a way, basically what we're doing is, in a way, the way we design concrete beam is then, okay, if I look at the beam from there, from the front, this is the beam. This is the reinforcement. Maybe I only have two reinforcement. Okay, basically anything below the neutral axis, any concrete, we ignore the concrete here. We ignore the concrete here. Okay, in design, we ignore the concrete there. We use the reinforcement to take all the tensile forces. Okay, we use the reinforcement to take all the tensile forces in the tensile zone. Okay, so concrete ignored in tension zone. Okay, we ignore, we pretend the concrete is not there. So in a way, we design it like this. If this is the neutral axis, we assume we have concrete at the top. We assume we don't have concrete at the bottom, just the two reinforcement. Okay, that's basically how we design it. Yeah, we assume we have concrete at the top of the neutral axis, but below neutral axis, we ignore the concrete. We pretend the concrete is not there. We use the reinforcement to carry everything. Okay, that's how we do the design. Later on, you will see that's basically how we do the design. Okay. Okay, the next thing, this is more like a simplification. Okay. Plane sections remain plane. Okay. In other words, there is a linear distribution of strain. Okay, so we assume that the distribution of strain is linear, because if it's not, it's very difficult to calculate later. Okay, it's very difficult to do analysis if it's not. We do some simplification lah, okay, of the actual behavior. Okay, so next we talk about the stress block. Okay, before I talk about the stress block, I just want to ask a question. Everyone, do you know what is a neutral axis? I just want to make sure you know what neutral axis is before I go too far. Do you know what is a neutral axis? Huh? Do you know what is a neutral axis? Someone?
Sir.
Yeah.
Is it imaginary line for
Yes, correct. It's imaginary line, correct?
for the where the tension or the compression happens?
Okay. Not quite, but it's basically okay. It's like this. So neutral axis is what? Okay. So you have your beam. So your beam is bending. Okay. Now, when a beam goes into bending, I mentioned the top is in compression, right? The bottom is in tension. Okay. Now, so you have to ask yourself the question. Okay, top tension, top compression, bottom tension. Where does it change? Yeah. Where does it actually change? The stress. So we know at the bottom, we know at the top, we have some compression, compressive stress. I don't know, maybe 10 MPa compressive stress. At the bottom, maybe we have 10 MPa tensile stress. Now, where does it change from compression to tension? It has to change somewhere. So normally what happens is the stress in the beam starts to get lower. It starts to reduce as you get closer to the middle of the middle of the beam. At some point, it's going to cross over to tension. So the neutral axis is where this happens, where the stress is zero, basically zero. Yeah. And the compressive stress changes to tensile or vice versa. Yeah, it's basically where the stress is zero. From compressive strength, from compressive stress of 10, it slowly reduces until the compressive stress is zero, and then it starts turning into tension and keeps increasing to the bottom. Okay, so the neutral axis is the height at where this stress is zero, where it converts itself from tension to compression or from compression to tension. Okay, understood? Is that clear?
Doctor. Yeah, clear.
Okay, all right. Okay, so this is important. Neutral axis is important. Okay, next. Next, I'm going to start drawing a few diagrams. This is basically the stress distribution diagram. Okay, Do you need to know this? I'm trying to think. Yeah, I'm gonna just explain it quickly. Okay. Good if you can understand, but if you can't follow, it's important for the basics. Yeah. I'll try to make it understandable. Okay, let's say I have your concrete beam. You have some reinforcement at the bottom. Okay. Now, as I explained last week, you also need some reinforcement at the top sometimes because the tension can move from bottom to the top. Okay. For continuous beam, sometimes the tension is at the top. So you need to allow for reinforcement at the top. Okay. So this is your normal concrete beam, but the biggest one is at the bottom. The biggest reinforcement is at the bottom. You just consider the bottom one for now. Okay. Okay. So this is your cross section of your concrete beam. Now, from the reinforcement to the bottom, we call it the cover. I think I taught you how to calculate the cover. This is the cover. Yeah. Towards the end of last week, I went through the cover with you, how to calculate the cover. It's C min plus 10 millimeter. Yeah. C min plus delta C. You remember? Okay. So that is the cover to protect reinforcement from corrosion, basically. Okay. To protect. So the cover is to protect reinforcement. From corrosion or fire or acid in the ground, things like that, okay, to protect the reinforcement. So it's a sacrificial concrete. So basically that height of concrete, we also pretend it's not there. We pretend no concrete for design. For calculation, we pretend it's not there. We pretend there's no concrete there. Okay, because it's a sacrificial layer used to protect the reinforcement. Okay. Next is the remaining height above. We call it D. Okay, this is the design height of the concrete. The rest of it, okay, we call it D. Okay. Next, we have AS, which is the area of the reinforcement. Yeah, you see the two red dots. The two red dots, the reinforcement. AS is the area. It's basically the area of the left reinforcement plus the right reinforcement. You add it up, you get the area. Okay. Next, you have AS dash. AS dash. AS dash is the area of reinforcement for the top reinforcement. Okay. So AS is area of reinforcement. AS dash is the area of reinforcement for the top reinforcement. Okay. Now, next, we get to the strain. Okay, to the strain. So we need to know the strain diagram now. So for this section, the neutral axis will be somewhere there. Okay, neutral axis. Okay, so your strain will look something like this. Okay, now you stop. We stop here. Oops, I drawn too much. You stop at the bottom reinforcement. Okay. Like that. Okay. So we pretend there's nothing below the reinforcement. Okay. So that's a strain diagram. So the bottom part, we call it epsilon st. So epsilon st is strain in the steel, in tension. Okay, because at the bottom we are dealing with the steel reinforcement. Okay, at the top, okay, we are dealing with concrete, sigma cc. So basically the approach is this. Okay, at the top, I told you it's in compression. So in compression, when the beam is in compression, compression is taken by the concrete. We use concrete to resist the compression, but the tension at the bottom is taken by the steel only. We ignore concrete at the bottom, okay? As what I've drawn earlier, there, yeah? This diagram here. At the top, we have concrete. At the bottom, we pretend no concrete, only steel, okay? We use concrete to resist compression. Let me just write it down here. We use concrete to resist the compression. And we use the steel reinforcement to resist tension. Okay. Okay. So which is why for your strain diagram, at the bottom, I have a T. Oh no, sorry. At the bottom, I have an S. I have S for steel, T for tension. At the top, I have a C for concrete, and I have a second C for compression. Okay? That's where the subscripts come from. Okay, now there is another one. Now, sometimes, as I said, we need to put reinforcement at the top as well. Okay, because the beam goes into tension at the top when it's a continuous beam. Okay, now there are also certain events where the concrete is not strong enough for compression as well. Sometimes when the beam is heavily loaded, sometimes even the concrete cannot take all the compression at the top. So we need to put compression steel. Okay, we need to put compression steel sometimes. Okay, I will let you know later when. Okay, so we need to design a layer as well called epsilon SC for steel to resist compression. Okay, but this is not always the case. This is only needed sometimes. Okay, so this is a strain diagram. Okay, so the height of the AS dash of the compression steel is D dash. Okay, so we have two Ds. We have a D here, and then we have a D dash. We have a D dash there for the AS. Okay, so AS. So AS we measure using D. AS dash we measure using D dash. Okay, there. It's all measured from the top of the beam. Okay, measured from the top of the beam. Okay, next, the stress diagram. Okay, next, the stress diagram. There's a stress diagram that looks like this, triangular. This stress diagram is used for SLS condition only. So when you're checking crack width or deflection. Okay, when you're checking crack width or deflection, you use this type of stress diagram. Okay, however, when you're doing reinforcement design, you actually supposed to use this one. This one. This is parabolic. Okay, so at the bottom is parabolic. Okay, so this diagram is called rectangular parabolic stress diagram. This is used for ULS design to represent stress distribution at failure. Okay, at failure. So when we design at failure so that we can prevent the failure. Okay, we need to know when it's going to fail. Then we design to prevent that failure. Okay, so that's why when we design, we always design at failure. Okay, now there's a problem here. When we calculate the stress, we basically calculate how do I know what the stress is here? Huh? How do I know the stress there? Or rather the resultant force. This is a stress diagram. This thing is a stress diagram. The stress here may be, I don't know, 10 MPa. Okay, but sooner or later, I need to calculate a resultant force. I need to turn this stress into a force. How do I do it? I need to calculate the area. The area is the force. Okay, now how do you calculate a parabolic area? You can using computer, but using hand calculation is very difficult. Very difficult to calculate a parabolic area. So what they came up with then is a third one, C. Okay, a rectangular equivalent. A rectangular equivalent of B. So this is also ULS, but for design. They basically simplify it. Okay, they simplify B. They simplify this parabolic one so that you can use it in design. How do they simplify it? They basically say, okay, we add up the whole area. It's actually going to look something like this. Like this. Okay. So basically they rearrange. They rearrange the B parabolic into a rectangle so that it's easier for you to calculate. Okay. But it's now smaller lah. Okay, because they take some of the they take some of the area below and then they move it to the top. Then they try to optimize everything into basically a rectangle. Okay, so this is the neutral axis. Okay, so how do you calculate this area? This height they calculated is roughly, they call it S. So this height is called S. It's roughly 0.8x. Okay, 0.8x. Okay, x is this distance, the original distance from the top of the beam to the neutral axis is x. Okay, so they basically say, okay, if we have to simplify the parabola into a rectangle, it's about 0.8 the height lah. Yeah. Okay. Okay, more formulas. So today I'm gonna go through with you the theory. Okay, go through with you the theory. Tomorrow we will do examples. Then it will be clear. Okay, then it will be clear. So the way I teach RCD is very similar to calculus. I go through theory with you first, and then I'm gonna go through a lot of examples. Okay. Now, as there is compatibility of stress, of strains between the rebar, reinforcement, and adjacent concrete, the steel strains epsilon st in tension and epsilon cc, which is concrete, in compression. Can be determined from, the strain diagram. Okay, so from this diagram, basically from this diagram, you can come up with this relationship. Okay, you can come up with this relationship. On the left side is steel in tension. On the right side is the concrete in compression. Okay, now at maximum concrete strain, epsilon cc becomes epsilon cu2, okay, which is the 0.0035. Okay, so you replace epsilon cc. Yeah, so you replace epsilon cc with epsilon cu2 x. Okay, and then you can rearrange everything to get steel strain in tension. Epsilon st, which is you rearrange everything, move everything to the right of the formula. Therefore, epsilon st is equals to epsilon cu2 d minus x divided by x. Okay. This is, we call it the first formula. Okay. Now next, the steel strain in compression, epsilon sc, okay, is epsilon cu2 x minus, okay, sorry. From the diagram, again from the diagram, you can also come up with this formula. Epsilon sc is equals to epsilon cu2 x. Okay, from this diagram. From this diagram. Okay, you can come up with this relationship. Okay, so you can arrange this relationship to get the steel strain in compression, epsilon sc, which is epsilon cu2 x minus d dash divided by x. Divided by x. Okay, this can be the second equation. Okay. Okay. Do you need me to slow down, or are you managed to copy everything?
No, we managed to copy, inshallah.
Okay, all right, thank you. Okay, therefore, we take equation one. Okay, take equation one. You take equation one, you can rearrange equation one also to get x, which is d1 plus epsilon st divided by epsilon cu2. Let's call this equation 3. Okay. Now, we know at at ULS, ultimate limit state, the maximum strain in concrete at failure, epsilon Cu2 is 0.0035. Okay, for anything less than or equals to C5060. For concrete grade C5060, okay, 0.035, 0.0035, okay. Where is this from? You go back to earlier. Yeah, epsilon Cu2, here. Right at the beginning of the lecture, I've given it to you, 0. That's why I told you, remember this number, 0.0035, okay? That is at failure. Concrete failure, okay? That is the strain, okay? Okay, let's go back here. Okay, and then for steel, you remember what it is? Yield strain. Oh, for steel, yeah, for steel. For 500 MPa rebar, what is the yield strain? I mentioned it earlier. Nah. When the steel has yielded, what is it? 0.00217. Okay. Okay. So now you put this in here. You put the bottom one in there. You basically get x equals to d divided by 1 plus 0.00217 divided by 0.0035. You basically get 0.617d. Okay, so x is equals to 0.617d. Okay, now this is when this is when the section has yielded. Okay, yielded. Yeah. Okay. Yeah. So you remember the strain, the maximum strain in concrete is this. I use the yield strain in concrete. I use the yield strain in steel. So calculating it, I get 0.617. This is when the section has yielded at failure. This is X at failure. Okay. So therefore, to ensure yielding of tension steel at ULS, we have to always make sure X is less than or equals to 0.617D. Okay, this is the point of this formula. Remember this formula as well. Okay, remember this formula as well. Okay. Okay. Okay, we'll stop the class here. The rest I will go through with you tomorrow, face to face. Okay. Before you go, wait, give me a minute. I need to do attendance. Don't leave. Wait for me.